if you went back and looked at the Marginal Revolution University videos dealing with the solo model, you should be ready to grasp the intuition of the crazy algebra that we're going to do today. Today, though, we're going to start to build what's called the solo swan model for economic growth. Solo and Swan sort of discovered or developed these ideas independent of one another, sort of the way that Leibniz and Newton developed the ideas surrounding calculus independent of one another. And we start with the same thing we've kind of been starting with, this production function. We have capital and labor, and we're going to use capital and labor to make stuff. And there are people that own capital, and there are people that own labor. And then there's this assumption about constant returns to scale. So the idea is that as we change the amount of capital and labor together, proportionately, our output changes in the same proportion. So the way that that's shown is that f of z times k and z times L, if we augment capital and labor by the same amount, or proportionately, then the output changes in the same proportion. So if we have 10% more capital and 10% more labor, what comes out is 10% more of everything. This assumption is called the constant returns to scale assumption. And the reason why we do this in functional notation is because there's a lot of different forms that that function can take. There's a lot of different algebraic forms that that function can take, and we're leaving that sort of in the black box for now. We're making this assumption so that the manipulations that we do to this basic formula remain true throughout. Now, those of you that are super mathy are going to be pleased by this assumption. The rest of you are like, who cares? And I'm amongst the who cares crowd. Now, the first thing that we do to this equation is we try to find the effective impact of each variable. And the way we do that is we say, we have a certain amount of output. Well, how much does each person get, or each worker get, or does each worker produce? This is the get side, right? And if we go back to this function, we can divide each portion of that function, K over L, and L over L. Again, notice what I've done is I have z'd everything. So I did 1 divided by L times K, 1 divided by L times L, and I get Y times 1 divided by L. So we needed this sort of assumption to get this result. And I can simplify this, and I get Y over L equals whatever our production function is, K divided by L, comma, 1. Because L divided by L is 1. This allows me to simplify the function and just say, well, since 1 is always going to be 1, then it doesn't matter how I change the other variables. This is going to remain 1. It's going to remain a constant. It could have been a constant of 50. Who cares what the constant is? Because we're thinking about this in terms of marginal changes. And marginal changes are typically arrived at through taking the first derivative of something. And what's the first derivative of 1? Nothing. Right? It falls out. It's a constant. So 1 doesn't change, so the first derivative is nothing. There's no change to 1. So that's why we do this initially. Is we divide both sides by L so that we can get 1 here and simplify the right-hand side of our function. Now we take Y over L and define it. So the 3 lines, is a 3-line equal sign means an identity. We define it to be little y. Or y, little y. And then we define K over L to be little k. And I actually have a really hard time drawing convincing little k's. So I use cursive to do it. You can use an italics to indicate it. But This is how the textbook does it. And the idea here is that this is the output per worker. This is how much output there is divided by the number of workers. So this is output per worker. And this is capital per worker. You can think about that like, okay, suppose you've got a landscaping crew that goes out and does all the yard work. How many lawnmowers do you have per worker? Does each worker have his own or her own lawnmower? How many leaf blowers do you have? Do you have a tool for each person to use, or do they take turns using the tools? I don't know. But this is what that's trying to get at, is how much capital each person has. Now each person, when they use some capital, augments their labor with that capital and is able to produce more. So we're interested in how much capital there is per worker because we want to know how much more productive each person is when they have more capital. So then I can take this general function that has become this, and I can throw in these variables for this variable and this variable, and I get little y is equal to little f times, or function of little k. Remember, this drops out, okay? And we're left with a much more simple function that we're going to take through the next several steps. The first step is to say, well, okay, what happens when we add a little bit more capital? Or in other words, what is the marginal product of capital? And we can define the marginal product of capital to be the output of one more unit of capital minus the output of however much capital we had to begin with. So this is how much capital we started with. We're going to add one more unit of capital. How much more stuff did we get out of it? By adding one more unit of capital, more stuff, that's the marginal product of capital. A little bit more capital, a little bit more stuff coming out. And we think about that in terms of a graph that looks like this. This is the function f of little k. And we have different amounts of capital and different amounts of output, little y. Add one more unit of capital. And then the question is, how much more output do we get out of that? All right, and so this is the marginal product of an additional unit of capital. Or in other words, it is the slope between here and here. I got through one page. I don't know ways. Okay, so we're going to remember that little y is output per worker, and little k is the capital per worker. We're going to add some more definitions. We're going to say that little c is consumption per worker. And little I, I'll put it in here, little I is investment per worker, or capital I divided by L. Do not confuse the little I that I'm using in this context with the little I which I was using to indicate the nominal interest rate. Why do I use I for both? Because econ. All right, and since I'm so good at explaining all of this, I have to find ways to try to confuse you. No, it's just the way it is. Okay. You're dreaming, Snow. Okay, and then let's also add in here a little s. And little s is the percentage or the share of income that each worker saves. Now, there's a couple problems. So far, I haven't included anything having to do with unemployment. I haven't talked about people who aren't workers. I haven't changed the number of workers yet. If we get to it, we will change the number of workers later. Also, there's no international trade in this market so far. So it's a closed economy. There's no NX or issue having to do with imports and exports. We're going to keep it simple and not bring that into this model for now. Okay, so we've got our definitions. Now, does it make sense to you that Y, the amount of output per worker, would be equal to the consumption that each worker engages in plus the investment that each worker does? Right, this is similar to the consumption and saving kind of combination. Whatever they don't consume, they invest. So we're also assuming perfect investment. Okay, that everything that doesn't get consumed gets invested. None of it lands under the mattress. By the way, little s, since it's a percentage, this is a number between 0 and 1. It's helpful to define that mathematically so that we don't make mistakes later on. Now, what is consumption? The amount that we consume can be referred to as a share of, or the 1 minus the share of our income that each worker saves. In that case, then Y would be equal to 1 minus savings rate times, not C, but Y. Plus whatever gets invested in. So this substitutes for this. Can you see whether I'm getting that part on the camera?
Yeah.
Okay. How far can I go here?
No.
So I'm at the limit already.
Yeah.
Let's just call that the limit. Okay. And your textbook just says, and this turns into something else. I'm going to try to walk through that a little bit here for you. So Y equals Y minus SY, distributing the Y through, plus I. Did this right so far? Okay. If I subtract Y from both sides, and add SY to both sides, so minus Y, plus SY, plus SY, I get SY, these cancel, equals I. In other words, the amount that I save of my total income is the amount that I invest. Or the percentage of my total income is the amount that I invest. And the textbook rearranges that simply to say that I is equal to SY. Investment here is equal to, the amount that gets invested is equal to the share of our income that we save. Okay, so we have our production function, which is simply Y equals F of K. We have our consumption function. What we consume is Y times 1 minus S. And the idea here is that, what do we do with our savings when we save something? Well, we buy capital with it. All the money goes to investment that buys capital. So if I equals S of Y, and Y equals F of K, then we can say that I equals the amount that we save out of what we produce given a certain amount of capital per worker. Given this amount of capital per worker, they produce stuff, this is production, and we save a share of whatever it is that we produce, and that is the amount that we end up investing. On our solo model graph, the way this gets shown is that if we're producing this amount, then at every amount that gets produced, a constant share of it is what we save. so that, if right here, this is equal to 10% of the total, then here, this is also equal to 10% of it. It looks more like 50%. Every way that I've drawn it. So we save a constant ratio of what we produce. Now, Keynes's model doesn't do that, right? There's a marginal propensity to save in Keynes that adjusts. This model doesn't have that. I got through 2 pages. What do we need now? It seems pretty simple so far, ha ha ha, so we should definitely complicate it. I'm going to throw another variable in here. That is a delta, or a lowercase Greek d. We draw it by doing a circle and then putting a tail on it. This is the rate of depreciation. Of capital. And capital wears out, doesn't it? Of course it does. You got a car, eventually it rusts. You buy a pair of shoes, eventually the leather wears off the bottom of them. Capital wears out at what rate? Well, we're going to assume that the rate of depreciation in terms of its value is relatively constant for all different goods and services, particularly forms of capital in the economy. Again, big picture here, what are we making? What is the thing that we're actually producing in this model? GDP, as if there were a GDP that you could consume. That's sort of how we're treating it though. We're talking about the GDP factory in all of this. So for example, if your capital, if you own a machine and it lasts for 25 years, we would say that the rate of depreciation is 0.04. Okay, that every year it wears out by about 4%. And after 25 years, the last 4% wears out and it's gone. Are you with me? Or whatever your total stock of capital, though, is going to be depreciating by 4% every year. All of the machines are depreciating at that rate. And notice, this variable is just a number. It's not a function of anything. It's just a number, which is to say that it is a straight line. Mathematically, it's constructed as a straight line. The way we show that on this graph is just to say del. Right? The rate of depreciation is a straight line. Now, what happens here? We'll call this actually del. Okay. The rate is del. When the capital depreciates by del K every year. Well, how then does capital change over time? How does capital, the amount of capital per worker, change? We know that investing in capital buys more capital for the next year. But at the same time, the amount of capital that is in existence is wearing out at a certain rate. So we can construct an equation. The change in the amount of capital is equal to the amount of capital that you buy every year minus the rate at which the existing capital is wearing out. Now we already have a definition for investment. It's SY, and furthermore, it's S of F of K. So we can substitute this in for that. And so then the change in capital per worker is equal to the savings rate of whatever it is that we are producing minus the rate at which the capital that we have is wearing out. We would want to try to find the point at which adding another unit of capital doesn't benefit anyone. Or in other words, we want to find the point at which investment in capital has reached an equilibrium point. That is to say that on this graph, if my savings rate is lower than my rate of depreciation, then next year there is going to be less capital in my economy than there was this year. If the rate at which I am investing, so the amount of output that goes to additional capital is less than the rate at which that capital is wearing out, then next year I'm going to have less capital. If the savings rate is greater than the depreciation rate, then next year I'm going to have more capital than I have this year. So then the amount of capital in a market or in a given economy gravitates towards an equilibrium. That equilibrium is called the steady state. Because it's an equilibrium. If we start out to the left of here, we're going to move to the right. If we start out from the right of here, we're going to move to the left. And that is denoted as K star, the steady state quantity of capital. At the steady state, the change in capital is 0. Next year, there won't be any more capital or any less capital than there was this year when we arrive at the steady state. So then, on the left-hand side of that equation, we're going to have a 0. So 0 equals S of f of k minus delta k. And we can move this around and get S of f of k equals delta k. Which is to say that the rate at which we're buying capital is equal to the rate at which capital is wearing out. To give it some sort of a concrete relation to the real world, we will take the Cobb-Douglas formula of this overall model. In other words, we're going to give it some actual functional form and see what happens. Instead of simply y equals some function of capital and labor, we'll actually give it some definition. Can we do this and make it work? How does this fall through algebraically? We start by dividing both sides by labor the same way we did before. Y divided by L is going to give me little y. Okay, and then on the right-hand side, I'll have k to the 1/2 times L to the 1/2 divided by L, which actually, if you have x to the 1/2 power divided by x to the 1 power, right, that's equal to x to the 1/2 minus 1, or x to the negative 1/2, or simply 1 over x to the 1/2. In other words, I end up with L to the 1/2 here. Or I end up with y equals k over L to the 1/2 power. Or I end up with y equals little k to the 1/2 power, because k over L is still equal to little k. So this is relatively simple when compared to the big functional stuff that I was doing earlier. And another way that you can think about this is simply to say that y is equal to the square root of k, which is what that means. Well, what would happen? Let's think about that in terms of this. Okay, so then we would have savings times the square root of capital is equal to depreciation times the amount of capital. If savings is 0.03 rather, and depreciation is equal to 1%, at what point will I achieve the steady state amount of capital? Or can I solve all of this for K? Sure I can. I guess you can multiply both sides by 10 to make the math a little easier, and I'm left with 3 square root of K is equal to 1K. If I divide both sides by square root of K, I get 3 equals K over square root of K. Am I doing this right? I feel like I'm doing something wrong. Nope, I'm good. I can multiply this by square root of K over square root of K. I'm left with 3 is equal to K times square root of K is square root of K. K times square root of K. Square root of K times square root of K is equal to K. So I'm left with 3 is equal to the square root of K. And then if I square both sides, I find out that K is equal to 9. In other words, if the savings rate for my economy, if my people in my economy are saving about 30% of their output, and if the output is depreciating at the rate of about 10% a year, I should find that my economy becomes stable with a quantity of 9 units of capital per worker. Now, there are a variety of different ways to solve any of these different equations to get to the same solution. I'm not going to go through another one right now, but there are different ways of getting to that. Now, one of the things that you learn from the Marginal Revolution University videos is that there are different economies in the world that are at different stages of development in terms of the purchasing of capital per worker. And an economy that has relatively little capital per worker will find itself at a point along the production function where the slope of this is relatively steep. The marginal productivity capital is relatively high here. That large marginal productivity of capital translates into a high growth rate. But as the economy adds more and more capital and develops further, it's increasing its output, but the marginal productivity of capital is becoming more and more flat, which is to say that the growth rate is becoming more and more flat. And so the United States has had a growth rate around 2.5% for a while, because we've perpetually, constantly kind of been at this level of growth. We've been for a very long time at a very high level of development. But after World War II, when we destroyed all of the capital in Europe and Asia, and by destroying all of the capital, I mean almost all of the capital in Europe and Asia was destroyed in World War II. The economies there found themselves at a point where they could have very high levels of growth because there was nothing there to begin with. And every additional unit of capital had a really high return. And so countries like Germany and Japan experienced really high levels of growth for a really long time. And today, they've arrived somewhere closer to where we are today. China, similarly, started out with very low capital per worker and still is somewhere between here and here, with a growth rate sometimes 10%, sometimes 7%. What should we expect over time? That the growth rate in China decreases and approaches a similar growth rate to the United States. Why? Assuming that the institutions are similar, if you're an investor and you've got some money and you want to make some money, you would be more interested in investing your money in capital where it has a higher rate of return, until it no longer has a higher rate of return. If this is a competitive process in terms of where people invest their money, they're going to invest where the rate of return is higher until it stops being higher. Now, some countries have low rates of growth, and they're stuck there. So some countries that actually have low amounts of capital and also have low rates of growth. That must mean that their production function is different. But something about that place is different. We get to that again later. In this basic model, we have a couple of different variables that can change. We could change the savings rate. If we change the savings rate, what happens? Currently, this economy has a steady state right here. But if we increase the savings rate, what happens? Well, as we increase the savings rate, we find that it comes to a new steady state at a higher level of overall output and a higher level of capital. That makes sense. People are saving more of their output. That means that more of it's getting invested. And then it'll arrive at a new steady state where output is related to the total amount of capital then. And notice as a result, okay, the total amount of capital changes and also the total level of output changes. What happens if the government starts to spend more money? This is bringing back in other models. But if the government spends more money and taxes go up, how does that affect savings? It could mean that there's less money to save. If there's less money to save, then the savings rate will fall. If the savings rate falls, the steady state of capital will fall, and as a result, total output will fall. Increasing of taxes can hurt the economy. It can hurt the growth side of the economy. Looking at the growth side of the economy is sort of thinking long run as compared to short run. It's often described as the supply side of the economy. So there's an entire school of macroeconomics that focuses on the supply side as compared to focusing on the demand side. What is the best steady state? Most people would say the best steady state is the steady state where I can consume the most. By adjusting the savings rate, we also adjust the gap between output and savings. This gap is how much we consume. By adjusting the steady state, or by adjusting the amount that we save, we arrive at different steady states, and different steady states will have different levels of consumption. We would probably want the level of consumption that was the highest level of consumption, not necessarily the highest level of output. What would that look like? Let's just consider this total level of output. At the steady state, we're in equilibrium between savings and depreciation. So then, if I find the point at which the rate of depreciation is equal to the marginal productivity of capital, in other words, if I take the first derivative of the production function and set it equal to the depreciation rate, I would get the highest amount of consumption. Everywhere to the left of this point, my level of consumption is smaller. Everywhere to the left of this point, my level of consumption is smaller. Maximizing my overall level of consumption would allow me to have the most stuff. And so that is reasonably what people would want. So then, we should expect that people choose a savings rate not consistent with a low level of consumption, or even with a higher level of consumption and a higher level of output, but instead the level of output that affords them the most consumption. This level of capital is even more interesting than just the steady state. This is called the golden rule steady state. The idea behind it being that at this level, we're consuming the most that we can, and we're providing the same level of consumption to our children into the future. And if I care just as much about my children as I care about myself, then I would want to do unto my children as I am doing unto myself. And doing unto others as you do unto yourself is called the golden rule, which you find in lots of different religious traditions. Also, utilitarianism as a philosophical tradition internalized this concept of the golden rule. And so it's not surprising that an economist, and economics has a very close relationship to utilitarianism, though it need not necessarily, it is not terribly surprising that an economist would find a solution consistent with that kind of a philosophical principle. Is it the only principle? No. But this is one that might work, and one that we might expect. Do we actually see it? Not so much. We don't see this all that often. Now, Mankiw, in describing all this, assumes a benevolent policymaker who chooses the level of savings in the economy such that we arrive at the golden rule. I do not like the way that he talks about this at all. I almost don't approve. Why do we need a benevolent policymaker to choose this? Isn't what we actually choose enough of an indication about what we actually want to show what our personal preferences are between consumption now and consumption later? I think so. Another way to think about it is that there's an invisible hand that guides us to this point, and that invisible hand has a feedback mechanism internal to itself that brings us to this point. You don't need to presume a benevolent policymaker to get there. It's just a shortcut, but one that imposes some ethical elements to it that I'm not completely comfortable with. How can I formalize this chunk of what I've done? I can remind myself that output is equal to consumption plus investment. I can rearrange this and say that consumption is equal to output minus investment. I can remind myself that output is equal to some function of capital, and at the steady state, we're going to put a star on it, that investment is equal to some level of depreciation times the steady state. Actually, I shouldn't put a parentheses around it, I should just multiply it. The parentheses is really trying to communicate that that what we're doing here is a functional kind of a thing. Then I can plug this and this into this. And I get that the steady state level of consumption is equal to output minus depreciation at the steady state, and then again with the parentheses in my notes. And I can be reminded that at the optimal level of consumption, it's going to maximize this difference. Well, maximizing is the same as kind of taking the first derivative. And if I take the first derivative with respect to the capital, I'm left with f prime of k star is equal to, or minus delta is equal to 0 at the maximum. And this term, the rate at which output is growing, is equal to what we have called the marginal productivity of capital. And so the marginal productivity of capital is equal to delta, is where we would reach the golden rule level of capital. Again, here's the marginal productivity of capital. Here's delta. And where the slope of this is equal to the slope of this distance is maximized, that distance being consumption. And the difference being what we invest. We can work through an example of this. Suppose again that the functional form of output is that y is equal to the square root of k. And that's helpful because that's what they use in the videos. If we let the rate of depreciation be 10%, then what can we do? We start with, I think I might have skipped a step earlier. I think I erased what I did have. It's going to take a minute to work through. The change in capital, effective capital, is equal to what we save and what we produce minus what wears out. Maximized S of f of k is equal to delta k. And that would give us k star when it's maximized. If I divide both sides by delta, and if I divide both sides by, make sure I'm doing this right, f of k, and what I'm left with is S over delta is equal to k star over f of k star. And if I use this and plug in, where did the number go? This as my function, and that is my delta, I can find out what the appropriate savings level should be. I can find out how much I should be saving. Do I need to include capital? Let's see what happens. Yeah, I do need a number for capital. I'm going to make it hung up at some point. If S over 0.1 is equal to K star over F of K star, and I want to solve for S, I'm going to substitute the square root of K in here. And what I can do is I can square both sides. I'm left with S squared over 0.01 is equal to K star. And that falls out because K star squared over the square root of K is K star squared over K, which is equal to K. And then I can multiply both sides by 100 to get this out of the denominator. So S squared equals 100 K star is that how I wanted to do that? No, that's wrong. One over 0.001 or 0.01 is equal to 1 over 1/100. Multiply this by 100 and this by 100, or multiply the whole thing by 1, and I'm left with 100. So what I have is 100 s squared equals k starred. And then I need at least some other information to find a solution here. And one that the textbook recommends is a marginal productivity of capital. Marginal productivity of capital equal to 1 over 2 square root of k. I'm getting very messy here and I apologize. If the marginal productivity of capital is equal to 1 over 2 square root of k, and at the golden state, that's equal to the rate of depreciation, then I can solve this for k. Solving this for k, I'm not going to try to use too much more time to do this, I don't have any more time. Solves for a steady state level of capital of 25. Plugging 25 in here, 100 times s squared equals 25. Take the square root of both sides. We end up with a savings rate of 0.5 or 50% being the golden rule rate of savings. Now, I'm sure I could do that much more prettily, and it's already worked out in the textbook. The intuition, what intuition should we gather from all of this? This model is simply trying to help us understand how capital influences economic growth and if there are limits to growth. Now, the limits to growth becomes an important question, not recently, not with Solow and Swan, but the limits to growth goes all the way back to Thomas Robert Malthus, a guy who lived just a generation after Adam Smith, and who predicted that we would overpopulate the earth, and that people would die as a result, that people would be starving to death as a result. There's some interesting elements of that I want to get into next time. Didn't have time for it today. The exam's only going to cover up through, I believe, chapter 7. And this is chapter 8. So the questions that you see on the homework are only through chapter 7. The exam is going to be October 23rd through 26th in that area, in that range of time, because I'm going out of town that weekend. So I'll have my GA proctor, or actually I guess I'm just going to have the exam be online. The exam is going to be multiple choice questions pertaining to the textbook, and then essay questions pertaining to the supplemental readings.